Welcome to Zero Knowledge. I'm your host, Anna Rose. In this podcast, we will be exploring the latest in zero-knowledge research and the decentralized web, as well as new paradigms that promise to change the way we interact and transact online. This week, I chat with Yi Sun from Axiom. He covers how Axiom works, what a coprocessor has been historically in computing, what it means to be a coprocessor to Ethereum, how ZKPs can be used to help bring historic data into smart contracts, and the new use cases that this can enable. Now, before we kick off, I do want to direct you to the ZK jobs board. There you'll find jobs from top teams working in ZK. So if you're looking for your next job opportunity, be sure to check it out. And if you're a team looking to find great talent, be sure to add your jobs to the jobs board today. I've added the link in the show notes. Now, Tanya will share a little bit about this week's sponsor.
Alio is a new Layer 1 blockchain that achieves the programmability of Ethereum, the privacy of Zcash, and the scalability of a rollup. If you're interested in building private applications, then check out Alio's programming language called Leo. Leo enables non-cryptographers to harness the power of ZKPs to deploy decentralized exchanges, hidden information games, regulated stablecoins, and more. Visit developer.alio.org to learn more. For questions, join their Discord at alio.org/Discord. So thanks again, Alio. And now, here's our episode.
Today I'm here with Yi Sun, co-founder of Axiom and recent guest of the ZK podcast. Welcome back, Yi.
Thanks for having me back on, Anna.
Yeah. Last time you were on, we actually did this episode about ML. It was, for me, a really important episode. I feel like I learned a lot. What we didn't cover in that episode, though, was Axiom, the project you're actually working on, or we just mentioned it in passing. And so, yeah, I wanted to have you back on to really talk about that.
Yeah, definitely. So we've been building Axiom for a little over a year now. And Axiom is building a ZK coprocessor for Ethereum.
Okay.
And what that means is that we allow smart contracts to do new things using ZK. So we let developers access historic data on-chain and use it in their smart contracts. And that wasn't possible before without using ZK to make that whole process trustless.
Got it. Let's talk a little bit about the sort of creation of Axiom. So in the previous episode that you were on, we did hear your bio and background. But yeah, maybe let's start that story again from the founding of Axiom. What is it? Who are the co-founders? How did it come together?
Yeah, so the origin of Axiom was really in a pretty concrete developer problem. So I was helping out a friend build a DeFi protocol called Anti-Finance. And Anti allows projects to commit to certain on-chain unit tests about whether, for example, for a lending protocol, assets will be greater than liabilities. And they had the very specific problem that they wanted the test to fail if at any point in the past, assets dip below liabilities. And so we were just thinking through whether this was possible for a smart contract. And we quickly realized it means smart contracts need to access history. So you can imagine my surprise when I realized that was not a possible operation.
Damn. Let's explore this idea of history. What do you mean by that?
Yeah, so essentially, if you look at what smart contracts can access on-chain today, when you go to the web front end for an on-chain application, you'll see lots of very informative data about, for example, for OpenSea, the historic owners of an NFT, all the transactions that have occurred, the price history. And if you try to circle which of those numbers actually OpenSea itself on-chain can access, you'll realize quickly that there's only one of those pieces of data, namely the current owner.
Yeah.
And so you realize from a smart contract point of view, the developer is actually quite limited in what it can do. And of course, developers today really mask that from the user by presenting it in a nice front end and hacking around the problem. But fundamentally, if you want to do things on-chain in a trust-minimized way, today you're quite limited.
Wow. So what are they doing in that case? Is it just like on a centralized server where they're just like every time there is a change, record is kept like in the kind of Web 2 way, but then, and it displays on the website, but actually if you were to try to like scan the blockchain today, you wouldn't necessarily easily be able to find it?
So if you scan the blockchain today, you could query all this information from an archive node.
Okay.
And I like to think that archive nodes exist to serve the human eyeball. So a developer queries archive node, puts it on their web front end, and the user can see the information. But what it's not good for is serving the smart contract.
I see.
So if you want to take, for example, the historic transaction data from OpenSea and do some on-chain operation as a consequence, that's very difficult today.
Got it. So you mentioned sort of the archival node. When you're dealing with a smart contract, it can't look into the contents of this node, can it?
Yeah, that's exactly right. So
Okay.
as a human, you can, of course, query an archive node, and you're implicitly sort of trusting that the archive node is sending you correct results. So when you see something on the Uniswap front end, that's what's happening.
Okay.
Now, a smart contract obviously can't query an archive node off-chain, and even if it could, well, it'd just be getting a number. And we all know on-chain, you're not supposed to just accept numbers that an arbitrary person put on-chain.
Okay. But then, so then how do you get this archival part? Like, if you're saying a smart contract can't do it, what can do it?
Yeah, so every blockchain has a unique twist, which is that the current block commits to the past block and the block before that, and so on. Mm-hmm. So actually, the current block contains a commitment to the entire history of the blockchain.
Yeah.
And if we were able to cryptographically reverse that commitment, we'd be able to give a cryptographic proof, namely via a chain of hashes, that any piece of historic information appeared in the history of Ethereum. Now, the catch is that verifying that proof is quite expensive. You might imagine if you want to prove something 1 million blocks ago, you have to present the 1 million intervening blocks.
Oh, wow.
Which is quite a bit of data.
Yeah. And in a smart contract context, you would never do something like this.
Yeah, that's exactly right.
Can't.
You
kind of.
basically can't.
Okay. But then is there anything that maybe not a smart contract, but something else can actually query to get that isn't so expensive?
So when you query an archive node, you can sometimes ask it to produce more data. It's called a light client proof. So that's something that lets you cryptographically verify that the piece of historic information it gave you is actually in the chain. Mm-hmm. And if you want to use that on-chain, you can try to verify that light client proof on-chain.
Okay.
So to reduce the expense, what we do at Axiom is to put that into ZK. So we use the synchronous property of zero-knowledge proofs to reduce the amount of data that has to be put on-chain to prove the access, and also to make the verification cheaper.
I recently met a developer named Tracy who is looking really closely at this space. And he was really kind enough to map out a little bit what this looks like. And what he had described was that the thing that's in the smart contract, the call, can't directly talk to this archival node. So instead, you're doing this separate call to the archival node. What is that called? What is that?
There's an optional extension to the JSON RPC API, which gives a call, which is ETH get proof.
Okay.
And actually, Alchemy and Infura both implement this call. And so it allows you to, in addition to requesting a piece of contract storage, you can accompany it with a Merkle proof that that storage value was actually committed to in the history of Ethereum.
I see. Is that very, very heavy? Is that not verifiable? What's wrong with just having that and then immediately writing that to chain?
Yeah, so it is verifiable. You basically check some hashes, but the difficulty is it's pretty large.
Okay.
And the cost of verifying these proofs adds up. So if you want to query one piece of historical data, you would have to verify this Merkle proof against a historic block hash.
I see.
And we can get into how you get these block hashes, which is its own thing.
Okay.
But suppose you wanted to query, let's say, 1,000 pieces of historic data. Now it's approximately 1 kilobyte per proof.
Okay.
A kilobyte times 1,000 is a megabyte, which quickly adds up.
So you're just saying you might be able to do this thing, but it would just be completely impossible if you were actually trying to do more than this one query, meaning it's very, very limited.
Yeah, that's exactly right. So if you think about most applications you actually want to do, you need to query quite a few pieces of on-chain data to really do anything.
So then are you creating sort of an intermediate interface or an intermediate environment? Do you have something that's hearing the smart contract going off-chain and then doing this query and then it goes back to it? Yeah, maybe describe a little bit what this looks like.
Yeah, that's exactly right. So when a developer wants to query into Axiom, they send us an API call that can either be just a standard off-chain REST API call, or they can emit an on-chain event which triggers us to fulfill the query. So on our side, we will look up the historic data and perform some post-processing and compute on top of it. Once we get the result, we generate a zero-knowledge proof that everything we did was kosher, that we fetched the right data and we did the compute correctly. And finally, we verify that proof on-chain in our smart contract and deposit the result for the on-chain application to use.
But in that case, I think you just said it. So say we're starting from a smart contract. Somebody writes a smart contract. They somehow in that smart contract ping you or access you. You then do the query. You then create a proof. You bring it back. But like, do you actually do something as well? Are you like changing the state in the Axiom environment?
We actually, in our smart contract, we have a list of verified results of queries. And so developers can read into our verified results and use that information downstream in their application.
To change state on the main chain.
Yeah, that's exactly right.
How do you force that though? Like I can't even really imagine is the smart contract written in a very specific way? Is it different than normal smart contracts? Or like, is there a different even like formatting if you're like sending code off chain? Or is that just like normal? I'm not a Solidity developer, so maybe it's just like a normal thing that always happens.
It's just a normal smart contract.
Okay.
So the difference is that everything we put into our smart contract, it has to be verified with a zero knowledge proof verifier that also occurs on chain in our contract. So it's very similar to how an Oracle works. So if you request, let's say, a price feed from Chainlink today, you make a request either off-chain or on-chain.
Okay.
Chainlink provides a fully trusted price on-chain, and then your application reads from that price from Chainlink's smart contract. The only difference with Axiom is that all the results we put on-chain, you don't have to trust us. We already have a proof that verifies that they are correct.
So you're replacing that trust with a ZKP. And are they also doing this like archival data, or is this actually also novel? The fact that you're like specifically focused on the historic data?
Yeah, we're focused on historic data because it allows us to verify it without any additional trust assumptions. So our philosophy is that anything you get from Axiom shouldn't impose any cryptographic assumptions beyond what you're already trusting on Ethereum.
Okay.
So any number we give you, you can think of it as the same as a number you read from a smart contract.
What kind of ZKPs are you actually using? Have you decided that?
We actually think of it pretty holistically. Today, we're using Halo 2 with the KZG backend. So we're using pretty standard snarks, and we're using lookup tables and custom gates. So the whole
ZK.
Modern toolbox of
Yeah.
ZK. But I actually think of building in ZK as maybe similar to operating in the early semiconductor industry. There are sort of new technologies to make ZK proofs all the time. You have to continually upgrade your backend to deliver better performance. And because the jumps are quite large, you really have to keep up or you'll be left behind.
How hard is it to update your snarks though?
It's honestly a question of art rather than science.
But like, do you have to redeploy the entire system every time? I'm guessing yes.
Yeah, you definitely have to redeploy the on-chain verifier.
Okay.
But we've designed our system to be somewhat modular. So we have a core system which serves the function of caching all block hashes of Ethereum from Genesis until the current block. And we have systems which call into that to verify user queries against those block hashes. So we can opt to upgrade pieces of that as needs arise or as we can deliver greater efficiencies.
In terms of the querying, like, are you running a full archival node as well in your system? Or is that like, are you pinging a stranger?
Right now, we're pinging, frankly, Infura.
Okay.
Eventually, we will run an archive node. But the beauty of our system is that the user doesn't have to care how we're producing the results because we're producing a proof that the results are correct. So to the user, we could have maybe done everything by pen and paper. So long as the proof verifies, they should be okay with the result.
Wait, yeah, how does the proof verify on-chain that it's correct? How does it know it's correct?
Yeah, so the key, that's a great question, actually. So whenever you verify a zero-knowledge proof, you have a root of trust, meaning that there's no sort of absolute truths about the chain. You really can only verify that if you believe that a certain block hash was present on Ethereum, then you should believe that it contains a commitment to some potentially very complex historic statement.
Okay.
So we always have to check that a claimed block hash for a specific block number actually was the block hash that occurred on Ethereum.
But when it's verified on-chain, it still can't look into the archival node, right?
Yeah, that's exactly right.
So you're basically relying on like the ZKP to say, because we're using the ZKP, this is why it's correct.
Yeah, that's right. The only aspect that the EVM provides to look into the Ethereum data structures themselves is the block hash opcode.
Okay. Oh, you can use, so there is a view from the smart contract on chain into just that.
That's right, just that. It's very
that's
limited.
what you're taking advantage of. Cool.
So you can see the last 256 block hashes, but nothing further.
Okay. That's interesting.
And we actually have to work very hard to extend that view from 256 block hashes back to Genesis.
Okay. Why do you use the term coprocessor? What is actually a like, is it mimicking something in computers? Like, where's that word coming from?
Yeah, you have to dig kind of into the dark history of semiconductors. Back in the day, before everything got integrated into CPUs, when you built a computer, you'd have your generic CPU processor, and then you would have different coprocessors that were specialized to different operations.
Okay.
So I went back on the internet and found a picture of actually a math coprocessor. So it was a coprocessor that allowed you to do floating point arithmetic faster.
Oh, wow.
And it was actually made by a company called MathCo.
Very nice.
So yeah, back in the day, you would buy like your processor and then you'd buy a coprocessor and hook them up. And so we think of our system as an analogy of that for smart contracts. So smart contracts are really good at doing synchronous small computations and accessing a small amount of data in a synchronous fashion. Whereas Axiom allows them to access huge amounts of data asynchronously and do kind of big computations on top.
What era, when you talk about that math chip, what era is that from?
I think the last one I was able to find was the early 90s.
Okay.
So from the 70s to the 90s, it was kind of a thing to have a coprocessor for your physical processor.
Do you think we can think about the blockchain as being in that state then, in a way? Like, are we 1985?
I actually...
like, in terms of what a computer looks like and how it works?
I went back to see what it, in terms of clock cycles, how fast is Ethereum?
Yeah.
And I think I concluded it was something pre-80s.
Whoa.
So definitely in the 70s.
Really?
And
I wonder, do you think that like actually developers in the space in general should be looking at those models to like sort of predict what other tooling will be needed? Or actually should we like not do that because maybe computers need to be rethought?
I think a combination is helpful. So blockchain computers are certainly extremely limited computers in some ways. And that's where I think looking at historical analogies can be helpful. On the other hand, the constraints of blockchain computing are pretty weird. For example, there's this distinction between synchronously accessing state and asynchronously accessing state, which doesn't quite exist on a standard, old school computer.
Why is that? Is it because of the decentralized nature? Because there's nodes everywhere and like information is flowing in different places? Or why does asynchronous not exist there?
Yeah, it's exactly this requirement for decentralization. So when you run a transaction on Ethereum, what's really happening is that all of the validating nodes on Ethereum are rerunning your transaction and coming to consensus about whether they ran the transaction correctly. So first of all, that's tremendously expensive. There's a 500,000x overhead. But secondly, you have to actually come to consensus every time. So when you run a synchronous transaction on Ethereum, you're paying that overhead. So what ZK is fundamentally allowing us to do is to run that transaction asynchronously.
Wow. When you say asynchronous, like, are you kind of saying that like the Axiom environment might actually be taking more time? Like, would it take, I don't know, 3 blocks where if you had tried to do something like this, it would normally be 1 and then it comes back 3 blocks later and changes the state? Is it like that or?
Yeah, we let you access way more information, but the price you pay is that you have to commit to some historic block at which you're reading that information. And once you're finished processing that block and generating the proof, you can put your conclusion on chain in a trustless way.
But it doesn't have to be the next block.
It doesn't have to be the next block.
And that's this asynchronous where like something can be happening over here and it comes back later.
That's exactly right. So you have to wait a little bit to process off chain.
Is there anything else from the main chain that you could be accessing? Like you've talked about historic data. Maybe that is the only thing that's there, but is there anything else that one could try to derive from these nodes?
We do want to access sort of all on-chain data. So today we offer access to block headers, account data, so your account balance, your nonce, and contract data.
Yeah.
And finally, local account storage. So we're in the process of adding transaction and receipt data, which would in particular give developers access to events.
Would it ever make sense to have like another node tier that like is analyzing these nodes? Maybe this is actually what this could be, where it itself becomes a source of truth that could be queried. Does that sound totally insane? You can totally be like, you're not a computer scientist. Stop suggesting stupid shit.
It's actually something we've thought about as being uniquely enabled by ZK. So at the beginning of the conversation, we mentioned that smart contracts can't read archive nodes.
Yeah.
But really, that's just because any read a smart contract does from an archive node would need to be accompanied with some type of proof. And at present, those proofs are huge and difficult to verify. So one vision we have for the future is to actually put an entire archive node in ZK. So imagine proving the correct execution of your full archive node.
Okay.
So that's a huge task. But if we were able to do that, we could serve every query from our archive node on-chain in a provable way.
Interesting. Would there ever be, I'm going to tell you a little bit more what I'm actually envisioning, which is almost like there's an analysis of historic data that's then stored in a new structure to always be easily queried, but like not that you'd have to run the computation each time. Could that exist?
Yeah,
is that sort of what you just described?
That's the direction we're going in. So we're thinking you could process the chain once and in a certain way. In a certain way. So imagine an archive node, but as a side effect, generating a zero knowledge proof of every step and recording those proofs in a ZK-friendly format. Once we're in that format, if a smart contract queries against it, we could return the result of the query much faster than the initial process of generating the proof.
Got it. Oh, this is cool.
And if you think about a normal archive node, that is kind of what it's doing. It listens to blocks, somehow processes them and ingests them into its database, and it can return queries to a user quickly. What we're thinking of doing is adding ZK over this whole layer.
Interesting. I've had another question just about Axiom, and not just Axiom, projects that I think fall in sort of a similar category. What are you? I mean, you're using the term coprocessor, but like in the ZK context, are you a tool? Are you another category? Are you like a platform, an environment? Like I've actually, when I do lists, if I list Axiom on it, it's sort of like ZK++ because I don't know what it is. What is it?
I would say we're somewhere in between a developer tool and a platform. So we intend ourselves to be used by smart contract developers who don't have to know anything about ZK. And the problem we think we're solving is that ZK can do many things, but it's really inaccessible to developers today. Like maybe if you're very interested, you can write circuits and get deep into ZK. But if you just want to build a more powerful and expressive application, there's really nothing there to help you use it today.
Yeah.
And we're just really focused on helping developers do more in their applications.
When you're writing those initial smart contracts, though, do you need to know a certain like syntax to communicate specifically with you? Or what's going on in that?
Yeah, we strive to make our smart contract interface as simple as possible. Developers, frankly, don't need to know anything about ZK. They just have to read from very standard Solidity data structures. And the trick is that the ZK is powering the fact that all of our results can be relied upon in a trustless fashion.
But like in the smart contract itself, it's just regular smart contract language. They're not like doing new things.
Yeah, just regular Solidity.
Okay. But is it true that like, say you're looking for like a historic piece, like there is no query currently to be done in a smart contract for the base chain. So like, is it just sort of a blob of text that's like not being read in the smart contract?
That's exactly right.
Okay.
So the query into Axiom is made to be interpreted off-chain.
I see.
So it's simply an off-chain REST API query or just a blob of encoded data that's emitted on-chain and interpreted off-chain.
Where in the smart contract is that? Is there a memo field? Like where does it go?
We intend for developers just to emit an event. So.
Okay, it's an event.
Yeah, so it's actually quite similar. We're mimicking an on-chain Oracle call. So when developers call into Chainlink, they either can hit Chainlink's off-chain server or also emit an event with their call.
I see. So you're kind of following that model.
Yeah, we think we just want to be as close to what developers are used to as possible.
In this example, though, like, so everything we've been talking about is sort of like getting a piece of data or getting some data, maybe range. But like, would you be able to calculate like an average over a period of time? Or like, can you actually do like a calculation on that? And kind of, to what extent can you do things?
In the beginning, we're offering very basic post-processing of data. So we can feed you arbitrary historic data and give you the Merkle root of that data, and developers can access that in a self-serve fashion today.
Okay.
We're also offering sort of custom ZK circuits to do specific processing that can enable specific powerful applications. What we're building in the future is a virtual machine that can layer on top of that and allow developers to specify compute in a query language on top of the data that they're accessing.
Where does the VM live?
So the VM is executed fully off-chain.
Okay.
And what's important is that the correct execution of the VM is proven in ZK off-chain.
Okay. And this is living, then the VM would live in the Axiom environment.
Yeah, that's right.
And how complicated could these processes be then? Like, how are the computation? Like, do you have an upper limit to what still could not be done, or do you feel like anything?
Yeah, we think what's kind of special about this co-processing setup is that there's no fundamental blockchain limitations to the computation you have to do.
Interesting.
So long as you can prove the validity of the computation in ZK, then you can use it on-chain. Whereas in, let's say, a rollup, you actually have these considerations. Like, should you be occupying all the block space of the rollup for your computation at the expense of others?
I actually was just about to ask you, like, what's the interaction then with a rollup? Like, I can imagine that you could live on a rollup.
Yeah, that's right.
But if you're able to like run computation and all it is writing a proof, are you then sort of competing with like the value proposition of a rollup? They're kind of saying that they're the environment for all of this computation because it's so cheap. But you're sort of saying like, well, actually, there's this VM where you could do a lot of the computation and you only have to write like a single proof.
Yeah, we think we're offering a really complementary type of computation from what rollups do. So we think rollups are really good for things like trading on an AMM. And that's very synchronous computation where the transaction right before you really affects your transaction. We're thinking of operations like performing a neural network inference or computing your on-chain reputation. These are things where it's a pretty long-running computation and it's relatively independent of other participants on the chain. So as you mentioned earlier, we can definitely serve rollups and we can also feed information from, let's say, ETH L1 to rollups.
You sort of mentioned earlier the light client. You're not building a light client, are you? Like, would you put yourself in a similar category as something like Succinct at all, the project? Because I, in the past, have lumped you guys together, but then realized, like, I don't know if you really are doing the same thing.
Yeah, I think we're pretty complementary. So Succinct,
also complementary, okay.
Yeah, Succinct is proving the Ethereum consensus. So it's really operating at the consensus layer. And we're taking the consensus as a given and verifying against the block hashes that consensus already agreed on.
I see. You're interacting with light clients, but you're not creating a light client of your own.
Yeah, that's right. We're using light clients, but we're not creating one.
I see.
And the reason is we don't want to impose any additional trust assumptions. So because we're verifying on Ethereum itself, if a user is willing to accept Ethereum, then we have a cryptographic equivalence between the data we're providing and what Ethereum itself provides.
Is there any sort of cross-chainness to this? Because as you're describing it, I'm sort of like, basically the smart contract would write from one rollup, and you could then actually, instead of querying like base chain rollup or base chain L1, you could just like query another rollup, and then you're delivering information back. Is that at all what you're doing? Like, are you kind of a bridge?
We're definitely not a bridge.
Okay, you don't want to be a bridge. Okay, not a bridge. Well, definitely not a token bridge, but like, are you a message passing bridge maybe?
I think we are part of a modular construction of a bridge.
I see.
So our perspective is that we're going to deliver what we view as objective facts. And we want our users to choose what sort of mechanism they want to use to bridge those facts between Ethereum and other chains or rollups. So in the case of rollups, there's a native bridge. And so there's not really much controversy over what to use. But we think for cross-chain applications, users all have their own favorite bridges. And what we want to do is verify facts on Ethereum, and users can choose how to port those facts to other chains.
I see. With the system that you've built today, you would never be querying the block headers of another chain for Ethereum. But you're only doing that query to the Ethereum chain, right?
Yeah, today we support reading from Ethereum mainnet and verifying against a block hash of Ethereum mainnet, and the user can choose what trust assumptions they want to put on that block hash. So if that's on Ethereum, we provide a way for them to access those block hashes fully trustlessly. If that's on a rollup, then the native bridge provides a way for them to access Ethereum block hashes. Now, if it's on another blockchain, then the user can choose what sort of bridge they use to get access to those block hashes.
Okay. Could someone build I guess they could build something like Axiom on another network. But I guess the thought is like, since most of the activity, I guess most of the interest is on Ethereum, that You wouldn't have as many queries that way.
Yeah, we can definitely support reading from any EVM equivalent chain. So that includes rollups or even alternative L1s. Right now, we're really focused on Ethereum mainnet. That's where most of the developers and users are.
Yeah.
But if that changes, we're definitely open to supporting developers where they are.
Have you looked into any of the other ecosystems about like how they would feed you historic data? Like, are other blockchains built differently than Ethereum? I assume so.
Yeah, we've done some basic investigation. Some blockchains are easier than others.
Okay.
So there are some chains like Near, where every block actually natively contains a commitment to all previous block hashes.
Okay.
And so that makes things a lot easier for us. Of course, we still have to adapt to their storage formats, but that's not a huge deal. Other blockchains like Solana have a much more complex way of committing to historic state. So there's no individual commitment to the full state. And so that's a lot more challenging for us to handle.
Interesting. But I guess like this, it sounds like you're not doing work in those directions right now anyway. You just sort of evaluated.
Yeah, right now we're really focused on sticking with the EVM.
Cool.
And we're starting with Ethereum mainnet, and we're thinking of adding rollups to start with.
Nice. I want to hear about potential use cases. Like we've talked just now about like the architecture and some of the where the information's going, but we haven't really talked much about like who uses this. Why do you use it? Why do you need this historic data? What does it actually enable? So yeah, like tell me a little bit about the kind of use cases that you're envisioning. Yeah, I'd be really curious to hear that.
Yeah, definitely. We're pretty excited about use cases that are fundamentally new and not possible without this access to historic data. One of the big patterns we like is enabling decentralized applications to have accountability. And what I mean by that is the whole purpose of a decentralized protocol is to coordinate the actions of some group of participants. And we think the most fundamental tool is to be able to reward good behavior and punish bad behavior.
What's bad behavior, though, in this case?
Bad behavior would be just anything slashable. So if you have a protocol, typically you want to slash people for doing something that's against your rules.
Your consensus rules.
Not necessarily consensus. It could be a decentralized application.
I see, okay.
Or it could be something that you don't want to put into consensus, but which you still consider to be bad. One example would be if you have some sort of consortium of validators or block producers, you might want to say, hey, we're like good block producers. We're not going to mine a sandwich attack. So maybe you could stake some collateral saying you're not going to do that. And we could prove like, hey, this producer mined a sandwich attack. They should be slashed.
But in the case here, bad is not like you are a hacker.
Yeah.
Like you can't undo that. You're not watching for that. If they're able to hack a smart contract and take funds, you can't like stop that.
That's right.
But it's more on the validators, the MEV side, it sounds like.
It could be sort of any on-chain protocol. Just as a different example where maybe the consequence is not slashing, if you have an on-chain asset management protocol, you want to see the performance of your asset managers. And typically you want to see things beyond just their profit at the end of the day. You want to see how much risk they took, what was the type of drawdown they had, and you might want to pay them or even potentially slash them based on what they actually did.
Interesting. So in this case, like this, I mean, I guess these are examples where historic data, accurate historic data, and nuanced, in-depth historic data is really interesting.
Yeah, we want to give developers more programmable control over how they design their applications. Today, you kind of have to bake your reward or punishment mechanism into the fundamental design of your smart contracts. And we think that if developers can do that much more flexibly, they can design just richer applications.
Can you imagine something like insurance becoming more on-chain? Because I'm just thinking like there have been these insurance protocols, but they're kind of clunky, it seems like. And I don't know that they're tracking things at that level. But there you could almost like decide like what is the rate of insurance based on actual historic behavior of some on-chain protocol or on-chain application.
I think there's sort of two directions we're interested in. One is underwriting. So if you can look at a user's historic behavior or look at a protocol's historic, loan to value, that might feed into some sort of machine learning system that determines the parameters of, let's say, your insurance protocol or even your lending protocol itself.
Wow. This is not a credit score, is it?
I don't think it's quite a credit score. Credit score comes with connotations of uncollateralized lending, which is tricky on chain. But I think of it more as underwriting. Okay. So if a protocol has set some risk parameters and they're doing quite well, maybe they can be a bit more aggressive with those parameters. Or if there's been a couple close calls, maybe you should have some autonomous system to back off a little bit.
What are some other use cases where you'd need that?
In another sort of DeFi setting, we sort of think that DeFi protocols today have very simple parameter sets on chain. And the reason is that they're not able to adjust them in a trustless fashion at high resolution. So in AMMs, they pretty much have a default set of fees. Whereas we think that fees should really depend on market conditions. If it's a very volatile market, maybe users should pay more for the privileges trading gets in AMM. Whereas if the market's not doing much, maybe the AMM needs to lower fees to incentivize trading. And so we think that there's a new generation of DeFi protocols that can be built using this awareness of historic information.
Yeah, that's interesting. Are there teams that have already shown interest in that? Or is it almost like because this tool is being developed, these new opportunities are there? Like, have you heard desire for that?
We've seen some teams essentially changing the parameters, but in a fully centralized way. So the team itself just changes the parameters. And
because they're looking at historic data like by eye.
Yeah, exactly. They're running some off-chain computer program, and they kind of pick the parameters. And sometimes this is called an oracle, and I don't think it's necessarily bad. But I do think that if it's switched to this more trustless model, they can change those parameters at a higher resolution and just more frequently.
What are some other like tangible, maybe like user-facing use cases that people might think about?
One big vertical we're really excited about right now is governance. So if you think about what's necessary for governance, the most fundamental object is voting. And to vote, you need to know how many votes you have.
Okay.
And so in a lot of settings on-chain, there are sort of DAOs that, for whatever reason, did not bake in the recording of how many votes everyone has into their smart contract.
Really?
And yeah, today they just can't vote. So one thing we're doing is building on-chain voting for a DAO that can't vote.
Whoa. Was this sort of like because this DAO was deployed a long time ago and like it's changed since then? Or is it like, is there some reason why that you can't calculate how many votes you have?
Essentially, that's the reason. So the smart contract for the DAO was deployed a long time ago, and they just weren't thinking of on-chain governance at the time.
Okay.
And it's obviously, you can't modify the smart contract now, and so we're helping them retroactively put that back in.
Oh, that's interesting. Is there some use case that sort of would be more focused on the identity front? Because even like that first use case where we talked about like insurance and stuff like this, I feel like there was something about like credibility, track record. So like, is there an identity play here?
Yeah, so we can let anything you do on chain be provable. And that ties into your identity in different ways. So today, if you collect an airdrop, you sort of claim to some protocol that you did a set of good actions and they should give you your airdrop, but it's fully centralized. The protocol team kind of looks on chain and sees what you did. We can envision a future where teams simply deploy a smart contract laying out the rules for what gets incentivized and what doesn't, and users can autonomously prove to the contract to get their token reward. In slightly less airdroppy fashion, we think that you can actually use this for user acquisition. So maybe I'm launching a new lending protocol and I want to just give better rates to users who have used a competing lending protocol.
Oh.
And we allow you to actually set those criteria in a pretty programmable way. So you can try whatever programs you want to attract users to your protocol.
Damn, the airdrop farmers are going to have such a hard time. They're just going to have to be doing everything all the time now.
Exactly. And the developers have some tools to fight back. You can set very fine-grained criteria.
Yeah. Huh. Any other ones? You keep mentioning inference ML. Is that one of the main focuses?
I wouldn't say it's a main focus, but we're pretty excited just to give developers better tools to adjust their applications on chain. And so for machine learning, we think it can be applied initially to DeFi. So if you want to change your lending rates or if you want to change your fee schedule, maybe you should be using some machine learning. So in traditional finance,
that's what
there
are
doing. Massive teams that trade based on very complex machine learning algorithms. But none of that is really possible in DeFi today. If you look at the code for an AMM, it's pretty straightforward.
Yeah.
Now,
in a way, when you say that too, does that mean like the predictive nature? Like it's using it to predict, right? It's like predict what the rate should be, not what it is according to today.
That's right. Today, what's on chain is a pretty crude approximation of what could be an ideal rate. And I don't think that you can necessarily deploy an autonomous model to get the ideal rate, but I think that you can make the on-chain systems a much closer approximation to a more efficient financial system.
Is there any future, like more complicated ML things that you can imagine?
Yeah, we're actually pretty excited about application of ML to NFTs.
Oh.
So there's this whole area of sort of generative art NFTs.
Yeah.
And if you look into it, you'll realize that there's nothing on-chain proving
that it's generative.
That it's actually generated from anything.
Uh-oh.
And so we think that we could tie the identity aspect to generative NFTs by allowing you to prove that an NFT was generated based on your on-chain activity. And so this would give sort of farming for the best looking NFT, like a new meaning. So you can imagine promotional NFTs. Like if you are a heavy Uniswap user, maybe you get an NFT that has more of a Uniswap theme, but interpreted through this generative algorithm.
That's neat. So like, since we're talking about ML, the last time you were on the show, that was the main topic. We were talking about works that you and Daniel had done. Obviously, those were like very specific machine learning plus ZK cases. But are you using like machine learning somewhere in the Axiom stack? Are you still engaging with that? Or are you just creating a platform for like use cases of ML?
At the product level, we really want developers to use ML on our platform.
Okay.
But actually within the development, we started using Copilot a couple months ago. Yeah. It's been pretty transformative.
Is it just faster? What's going on?
It's faster, and particularly for things like front-end development, it really fills in all the boilerplate.
Wow. This is GitHub, right? This is GitHub?
Yes, this is GitHub Copilot. I'm kind of a novice at it, but it's been incredible. If you haven't tried it, you definitely should.
And have you seen, like, I guess a lot of your engineers are doing it. Is your team just more productive? Do you notice it?
I think on more well-trodden types of programming, we definitely notice it. So on back-end APIs and front-end code, it's a big multiplier. On some of the circuit code and smart contracts, less so.
Okay.
And actually on smart contracts, we deliberately do not use it. Sometimes it hallucinates various lines of Solidity that are subtly wrong, and it's much harder to pick up those bugs when you didn't even write the code.
Oh, no.
So yeah, we're a little bit careful on the security critical parts, but on things like the front end, we're really excited to use it.
Cool. Just generally, like, what is the state of the Axiom product? Are you on testnet? Are you like, is there any sort of sense for when this will actually be usable?
Yeah, we put a demo out on mainnet in January. And the reason it's on mainnet instead of testnet is we're all about accessing history. And obviously there's no history on testnet.
Oh, yeah.
So you can go to our website today, demo.axiom.xyz, and you can check out a few toy apps we built on top. So we got a grant from the Uniswap Foundation to allow users to access Uniswap TWAP values in a trustless way through Axiom. And there's a couple other toys. You can prove your account age. We're working towards production release coming soon, and we'll have a couple of launch partners to share at that time.
Okay, cool. Where do you see sort of the general blockchain space going? Do you actually think we're on the precipice of like an explosion of computational power where like we could have on-chain games for real, or like on-chain, like big complicated programs? Or do you think we're still like just taking small steps towards that?
I think we're definitely getting some pretty big unlocks, at least at a conceptual and proof of concept level. I think what's missing is actually the developer tooling to allow developers that don't know anything about ZK or the other technologies going into it to actually access that power. And once we do that, I'm pretty excited about the new wave of trust minimized applications that's going to enable.
Do you think that, like, as you're saying this, I'm just thinking about like existing development suites or environments, something like Unity or something like huge. Is there ways that they could start to like interface? Would they just need to like add a few things to their system to be able to deploy some of this stuff on chain?
I think proving Unity on chain, that'd be awesome. I think we're a little far away.
Okay.
I feel the direction for that to happen is to be able to reuse some of their code and actually prove the execution of that code in some type of virtual machine. The difficulty today is that the performance hit you take by doing that is truly immense.
Okay.
And you kind of can't even think of using it in a similar fashion. I tend to think that the way...
We are still in the 70s, right?
Yeah,
That's
exactly.
what you said. Okay,
Unity
you're
was
right.
a 2000s
Yeah, we're not ready for
phenomenon.
it. Okay.
But I think what's exciting is applications typically have two pieces. One is the core business logic, and the rest is sort of user-facing stuff. And I think that applications will be re-architected to put the core business logic in some sort of trustless fashion on chain and have everything else done off chain. So imagine it as smart contracts on steroids.
Whoa, cool. I wondered, like, since you're here and the last time you were on, we did this ZKNML, I wanted to take a minute just to kind of recap what's happened. We're recording this beginning of May. You were on the show, I think, in February. What have you seen on that front, maybe outside of just the work you guys are doing, or maybe even outside of like Axiom specifically?
Yeah, I think there are a number of pretty exciting teams building in that space. So there's an open source framework called Ezekiel, which is trying to support sort of all manner of primitives for ZKML. And then Daniel has continued to work in that space. He recently open sourced his framework, which is called ZKML. And he's been using it to address a bunch of quite interesting models. So he recently snarked GPT-2, I believe. And then he also verified the Twitter algorithm in ZK.
I saw that. Actually, we'll link to those pieces in the show notes. We've been talking to Daniel a little bit about that idea of after zkpod.ai came out and I got kind of freaked out. It was like, is there ways that I could start to prove the, provenance of audio being recorded by me and like, actually released by me versus something like the AI's answers? Yeah, I mean, I hope that we get to see more on the audio front for that, because I know you guys had already done a lot of work on images, but seeing it in these different mediums, I think is going to be useful.
Yeah, and I think it'll be interesting to see where ZKML gets deployed. So there's always a question of the data provenance. So I think that can either come from some sort of a tested sensor, or if it comes on chain from some sort of proof that the data is actually validly read from the chain.
Yeah. That's crazy. What is the makeup of a team trying to enter ZKML at this time? Like I guess you need the ML experts, you need the ZK experts, you need the blockchain experts. But like, yeah, is this a very difficult to find combination, or are you seeing more groups like this pop up?
I think people coming into ZKML really come from one of two directions. One is you are already interested in blockchain applications and you want to apply ML to those applications. The other direction would be you're interested in trustless ML, and then you view blockchains as one potential application, but not necessarily the only one.
Do you think the fear that kind of emerged after GPT-4 came out, do you think that has also, like, I don't know, encouraged more people to look at ZK? I am curious how much ZK has even permeated the imagination of some of the ML people. Do they know about it?
I think very few of them know about it.
Okay.
We recently submitted our paper to a conference, and frankly, none of the reviewers have really thought about this concept too much.
Wow.
I do think what GPT-4 has brought into the public consciousness is a need for provenance in communications of all forms.
Yeah.
You see this with text and also with deepfakes and fake phone calls. And I actually think that blockchains and cryptography as a whole are sort of the way to solve this. Once you can't trust what you see with your eyes, really the only thing you can trust is some type of signature.
Yeah, I think it also plays, though, on the ID front. Like, you're going to need better ID and then the ZKPs along the way, because, like, that starting point, the thing that signs, also needs to somehow be yours. It has to for sure come from you. And this is where it's like, is this forcing an acceleration of these ideas that we thought were like kind of interesting and cool to like all of a sudden they're like actually needed?
It's definitely presenting the general population with the first real application where they actually want to verify whether something is real.
Yeah, it's pretty crazy. I still am due to do like an episode on zkpod.ai, which I don't know if listeners aren't familiar with it. Kobe has created a LLM of me speaking and him actually answering questions about ZK fed with the podcast transcripts. It's not perfect. You should check it out if you haven't seen it though. But yeah, like that's definitely brought it up for me. Like that was the big wake up call that like I had sort of these like fleeting, like, oh, maybe sometime in the future, this kind of thing could happen. And then all of a sudden it's like in front of me and I'm like, wow, this is now. I needed some tools yesterday that don't exist yet. And kind of amazingly, it's like our community, we're in a position to build some of these. It's kind of crazy. It's good.
There's definitely some urgency. Maybe in a few months, the episode will record itself.
Yeah. I mean, It's pretty messy still.
I
I
think
don't
you're
know.
safe.
I think I'm safe for a little while because zkpod.ai answers very confidently, not always correctly, and pronounces things sometimes strangely. But anyway, to wrap up, I do want to just ask you a little bit about ZK generally. You've sort of mentioned the sort of tech stack that you're using today and this idea of upgrading. But yeah, what's your take on ZK itself?
What we're seeing is a continuation of the really fast advancement in proof systems. And I think the feedback loop with actual applications is definitely helping. There's much more engineering going into these systems and really understanding their trade-offs. I would say that a really exciting recent idea is folding and accumulation schemes in general.
Yeah.
And this really started with the introduction of Nova, I think early 2022. And although Nova was really interesting, there are some limitations which prevented it from being applied very widely. And recently, there's been a flurry of papers, one a week almost, that remove a lot of those limitations and show that folding is more of a generic idea rather than Nova or supernova or hypernova being a specific scheme that you have to stick to. And so we're thinking through how that can be incorporated into our systems and what ways we can almost weaponize these ideas to produce the most efficient ZK proofs. I think it's actually very similar to the phase in between the introduction of Plonk in 2019 and the invention of sort of P lookup and ultra Plonk ultimately in the next few years.
Interesting.
Where people digested these ideas and realized they could be used in more creative ways.
Yeah, I've been thinking a lot about the sort of development pattern, and it does seem to almost be these like steps that are reached. There's no standard fully, or that step only lasts for a certain period of time. But it's like from step 1 to step 2, there's this flurry of research, all these different proving schemes, and then sort of like there's a settling around one. A lot of tools get built around that, built off that. You might get variations of that, and then there's these like this next step. Recently, I had Ariel Gabizon on, and we talked about these two kind of streams of thinking, which is like the accumulation advancements and then the lookup table advancements. And that like these are moving at kind of different paces. I don't know if there's been any like sort of proving systems that have unified them as effectively as they can, because sometimes they're using similar underpinnings, like in the KZG's additive homomorphism.
Yeah, I think there's sort of 3 really cool ideas coming in the space right now. There's sort of some check-based methods from Hyperplonk. There's sort of folding and IVC from Nova and its descendants. And then there's this idea of cached quotients for large lookups developed by Ariel and his collaborators. And I think we're sort of digesting to what extent they can be mixed and matched, what are the precise limitations, and how things will look in actual real-world engineering.
Yeah, because I mean, Hypernova does include some checks.
Exactly.
But as I understood, not much. And maybe there's more that could be incorporated, and you're going to get some interesting trade-off space there.
Yeah, and I think the space as a whole is undergoing that process faster and faster. I think people are realizing, hey, if we implement this very quickly, get some benchmarks, we know exactly what to do next, and that this iterative process is actually possible.
Yeah.
Like when Plonk came out, I don't think it was very obvious that you could just think more about the circle of ideas around Plonk and get much more out of it. And now everyone, I think, sort of knows that's possible.
Yeah.
And so with folding, it's sort of happening much faster with SumCheck as well.
One sort of, I don't know if I should say drawback, but maybe like challenge or threat to this model. Like, I think it's so exciting because we're seeing these like stepping points, but there is this idea or issue of like auditing these systems, knowing actually, are these libraries like super fully usable? If you think of the speed of the development, it's very, very exciting. People are very excited and into it, and you're bringing new minds to look at these problems. That's all good. But what is kind of sometimes a little scary is like you're having things built on things, and like there could be some primitives or some like ideas there that haven't been fully battle tested. And then you're all of a sudden layering on top of that like lots of value potentially. How do you think about that? Like, in a way, especially because like you're going to be using a ZKP that I'm assuming will have like some form of standardization at that moment. You're going to feel confident about it. But yeah, like how are you looking at that? How are you worried about that? Would you actually have an auditor audit the exact circuits that you're doing? Or would you kind of depend on the open source community there?
No, we definitely take security super seriously. And we think of it in many different dimensions. So first off, we are getting an audit, actually, where all our circuits are getting audited as we speak. And we're even getting the auditors to look at the verifier, which is actually the most crucial piece because it's the only thing that is deployed on chain.
Okay.
In terms of new proof systems, it is tough. I think it's very exciting to prototype very new proof systems, but I think as a space, we should be clear that it's very experimental.
Yeah.
It's important to prototype to get a sense for the performance, but I think when we go to production, we really want as many eyes as possible to look at it, both from the open source community and even from a more rigorous audit or a very formal write-up. Broadly, we think it's important to crystallize on what is the best expression of an idea and commit to formalizing that proof system and really devoting resources to that implementation. And I think with Plonk, we saw like Ultra Plonk be the final form, and many different teams are building production-ready implementations of that today. With Folding, I think it's still unclear.
Yeah.
And with some check and large lookups, that's also to be determined. I also think that audits aren't the end-all be-all of security. I think as a team looking to go to production, we want to be pretty deliberate. That's why we put our demo up with a ton of warnings. If you go to our website, it'll say, like, don't use this for anything valuable. And we think we want to climb the ladder of application value. We want to start with, things where even there's some issue, it's not a big deal, and only layer on things that are more valuable and could lose users money once we have a higher degree of battle testing.
Yeah. I mean, I think like just on my front, I've been thinking about like, how do we incentivize more of the white hat stuff and like disclosures and making sure that like people are incentivized to look deeply into these libraries, especially, I mean, it's sort of the challenge of open source in a way where it's like the maintenance. The maintenance in a way is making sure that these things are correct. But it's like less fun and you don't get rewarded really that much unless if you're an auditor and you're hired, that's one thing. But like, how do we get all of those eyes really spending the time to try to break these things before or break them ethically and share that? Yeah.
Yeah, there's definitely a bunch of work that people in running bug bounty programs or platforms like Immunify have done in smart contract space. And we're hopeful that they can be applied to ZK as well. One line of work that I think is really interesting in ZK, but quite early, is formal verification.
Of ZK circuits. Yeah, I've been hearing about this a little bit. Okay.
Yeah, so there's a company called Veradice that we played a small part in a paper they recently wrote on developing a DSL for SIRCOM that makes it easier to formally verify SIRCOM circuits.
Oh, wow.
And
it's a DSL for SIRCOM? It's DSL for a DSL?
It's a DSL squared.
Okay.
It forces you to write in this subset of SIRCOM that they kind of know how to formally verify.
I see. Okay. Oh, it's a subset. It's because, they've been able to check these ones completely. But is it a DSL?
It really is a DSL of a DSL.
Okay.
It is some new language which compiles to SIRCOM. and it's quite complex.
Nice.
But we think the pattern that it enables is really powerful because today as a developer, you kind of write some ZK circuits and you do your best. You test, you audit, you internally audit, you externally audit. But it's very hard to take effort and make your circuits more secure. Whereas formal verification, even if it's quite onerous, you can really put in some elbow grease. And if you get to something formally verified and your spec is clean, like you have a lot of confidence. So I think that's a really exciting direction.
That's really promising. Cool. Well, listen, thanks so much for coming on and sharing with us a little bit more about Axiom this time and sharing this little update on sort of what's going on in the ZKML space too.
Yeah. Thanks so much for having me, Anna.
Cool. And I want to say a big thank you to the podcast team, Henrik, Rachel, and Tanya, and to our listeners. Thanks for listening.